In this video, I want to talk about cooperative binding in hemoglobin. And what the cooperative binding in hemoglobin refers to is that hemoglobin molecules can bind 4 oxygens each. And each time hemoglobin binds an oxygen, it actually makes it easier for it to bind the next oxygen. So if we look at the percentage of oxygen in the environment, and we look at the saturation of hemoglobin, so it's like the amount of oxygen that's bound to your hemoglobin, what you'd find is that it's really hard to get that first one bound. And once you get the first one bound, now it gets steeper and then steeper and steeper. And what this causes is it causes the full saturation of hemoglobin at actually a surprisingly low percentage of oxygen in the environment. I think that it saturates around partial pressure of 80, and our atmosphere is generally about 115. So we've got a lot of wiggle room. However, what happens with this binding is that it can be affected by temperature or pH. If the environment is warm, then that's going to shift the binding this way, making it more difficult. And sometimes it actually makes it difficult enough that it's going to not even reach up here. At the very least, you'll need more oxygen to saturate your hemoglobin. In acidic environments, this same thing happens. And it turns out that the opposite is true. It's easier for hemoglobin to bind. It saturates at a much lower partial pressure at low temp or basic environments. So how do those acids and bases get there? Well, they get there through something called the law of mass action, or Le Chatelier's principle. But basically, it means that CO2 combined with water will have a reaction where it reversibly creates H+, this is acid, and HCO3-, which is a buffer that's used in your system. And this reaction wants balance. So when there's a lot of CO2 present, it shifts the reaction this way. It makes a lot more acid. And that's to sort of try to balance things out. When the CO2 drops, it shifts the reaction this way. It makes it a lot more basic. So this can be combined with a similar reaction. And in the similar reaction, we can see that hemoglobin binds oxygen, and that's a reversible binding. Again, this reaction wants to achieve balance. So when we get to your lungs, there's a lot of oxygen and not so much bound hemoglobin. So the reaction is going to shift. So the reaction is going to shift towards the bound state. It's going to bind that hemoglobin. Meanwhile, what's going to happen is at your lungs, there's a fair amount of CO2 trying to escape. And since the CO2 is escaping, that's going to shift this reaction this way, making it more basic, and it's going to make the oxygen more likely to bind to the hemoglobin. When we go to your skeletal tissues, the opposite is true. At your skeletal tissues, you get an increase in CO2, and that increase in CO2, moved my paper. You get an increase in CO2, and that increase in CO2 shifts the reaction this way, where there's acid. And this makes the environment very acidic. It makes the hemoglobin kind of unable to hold on to those oxygens. And meanwhile, what happens is you've got all this bound hemoglobin there, and that's going to shift it towards its unbound state where there's more free oxygen. So the hemoglobin actually has a couple reasons to let go of oxygen at your tissues and to pick it up at your lungs.